Let us start. I don't think anyone else is going to join. Is my screen visible? Can you unmute yourself to see whether the screen is visible or not?
Yes, sir. Screen is visible.
Okay, right. Actually, this is the tutorial for the third week for the NPTEL course of IC engines and gas turbines. And my name is Ananthakrishnan. I'm a PMRF scholar. I'm a Ph.D. candidate of IIT Delhi. So in today's session, we'll be looking at week 4 lectures, problems based on week 4 lectures. And these are the main topics on which the questions will be discussed for today's session. So mainly we will be looking at the initial portions, CA engine injection and SA engine injections, the lubricating theories, mechanical and electronic injection systems, battery ignition systems, and thermochemistry of fuels. We will be looking at the stoichiometric equations, how much will be the quantity of air required for fuel when it is in the stoichiometric ratio. So we'll be looking one problem on that, the thermochemistry of fuels, and mostly in this session it will be MCQ, multiple choice based questions, except two numerical questions. So we'll proceed into the questions. This is a lubrication based question. For a two-stroke engine, what will be the type of lubrication system used? So the options given are splash lubrication system, dry sum lubrication system, wet sum lubrication system, and mist lubrication system. Can anyone please tell what will be the answer for this question? The question is for a two-stroke engine. As you would have seen in the lecture for lubrication, they have discussed mainly about the four-stroke engines, where they mentioned about uh, pressure splash-based lubrication system and the pressurized lubrication system. But this is for a two-stroke engine, and it's a tricky question. Can anyone say what will be the answer for this question? Am I audible or not?
Yes, sir.
Okay, right, right.
Option A, mist lubrication system.
Right, right. Can you please say what will be the reason for that? So in the other case, the some lubrication systems, those are used for four-stroke engines. The answer splash lubrication system is used for four-stroke engines. So we can eliminate the possible wrong choices from it, and we can identify the answer. The answer is mist lubrication system, right? So it's used in two-stroke engines, mostly scooters, motorcycles, and all. It's a simplest form of lubricating systems. where the charge is compressed in the crankcase, right? So that charge what happens in the mist lubrication system is that the lubricating oil is mixed with the fuel. Uh, so rather than rather than providing a separate area for lubrication like splash lubrication or some lubrication, the lubricating oil itself will be provided along with the fuel. So that's why the oil and the fuel are mixed together and it is injected through a carburetor, and that will be trying to lubricate the piston cylinder arrangement. So in two-stroke engine we can't have it to be bulky, right? That's why we go for the minimum possible arrangement possible, and that is this mixed lubrication system where the fuel and lubricant will be mixed together. So the answer is mixed mixed lubrication systems. The second one, for the most automobiles, mostly four-stroke engines. What will be the common form of lubrication system used? Options are
B
splash
number.
lubrication. Yeah,
B number, sir.
right. Can you say what is the reason for it?
Don't know the reason, sir, but
Yes. So the splash lubrication system and pressure-based lubrication systems are the common form used. But mostly pressure-based systems, pressure-based lubrication systems are even more common than the splash-based system. Here, the lubricant will be passed through the lubricant oil. There will be a sump, just like the splash system. There will be a sump from where the oil will be pumped through different channels, and various distribution channels will be there, and through that it will be used for cooling, lubricating various bearings, crankshaft, piston cylinder arrangements. So compared to splash system where there is possibility of random splashing, pressure-based system will ensure that only the targeted areas will be lubricated, not randomly each and every points. So that is one added advantage, and we do not have the lubricant mixing with the air fuel mixture. So in the splash based system, there is a possibility that lubricant can mix with the air fuel mixer, and if it comes out of the exhaust gas, it can create emissions. So to prevent that, we go for pressure based systems where the lubricant will be mostly channeled to the area which is required to lubricate. So the answer for this question is pressure based system. Uh, so to prevent splashing and random mixing of Separate channels are being provided. Uh, and to flow this lubricant through the channels, pumping pressure should be there. External pumping power should be provided. That power will be taken from the crankshaft itself. So it will be a parasitic loss to operate the pump for the lubricant oil. So but compared to the splash systems, even then the pressurized system is used uh, because its advantages outweighs its limitations or disadvantages. Uh, the third question, it's regarding it's a continuation to the second problem. So the pressure inside the lubricant system will be controlled by oil pump, filter, relief valve, supply voltage. So what will be the mode in which the pressure inside the lubricant system will be controlled? Will it be controlled by a uh, pump or a filter or a relief valve or a supply voltage? So the answer uh, is a relief valve. So what happens is that the pressure inside the lubrication system is controlled by a relief valve. Uh, in the dry sump lubrication system, if the filter is clogged, the pressure relief valve opens, permitting oil to bypass the filter and reaches the supply tank. So in the case, if the oil filter gets clogged by some dust or impurities, there is also pressure building up and can be detrimental to the pump, which is high pressure pump, which is in used in the lubricating oil line. So to prevent that, we operate a relief valve which will bypass the oil and it goes back to its supply tank. So in the dry sump, okay. This is a different question compared to that of the lubrication system. This is regarding one kind of a loss. Um, why would we require crankcase ventilation? So, do you know, does anyone know what is crankcase ventilation? So the crankcase ventilation is a phenomenon in which the combustion gas produced in the cylinder escapes through the piston ring to the crankcase. So what happens is that it reduces when the piston moves from the top dead center to the bottom dead center in the power stroke, the amount of combustion gas present in the cylinder will be less compared to the normal case, thereby will be getting comparatively lesser power if this blow by happens. So in the case of blow by, what happens is that the air gas mixture after combustion just escapes the piston rings, goes to the crankcase, and the gas which is filled in the crankcase can be detrimental to the crankshaft. To prevent any harmful effect for the by the gases, we have to provide some kind of ventilation. So that is called a crankcase ventilation. So in this particular case, the real reason why crankcase ventilation is provided to remove the blow by. Blow by is the leakage of air, fuel, combusted products through the piston ring to the crankcase. So the answer to this problem is option D. So the explanation what I can give is, blow by the term means the leakage of fuel, combustion fuel air mixture, fuel air, rather it's combustion products. Leakage of products of combustion of fuel air mixture through the piston rings to the crankcase. So this is an issue, and to prevent that, we have to provide ventilation. We have to provide crankcase ventilation. An opening for the gas to go out to prevent these combustion products are anyway going to be high at high temperature and also high pressure, and that can damage the crankshaft and several other associated parts of IC engine. This is a question regarding the lubricant properties. Which of the following is the most important property of the lubricant? Density, thermal conductivity, viscosity, melting point. Can anyone answer this problem?
Viscosity, I guess, sir.
Right. Viscosity is the most important property of the lubricant. The main reason why the lubricant is being used is to smoothen out the sharp edges of the casted cylinder. So the cylinder's surface will not be smooth. It might be having some kind of protrusions, and that can create frictional effects that can cause friction and can the friction itself can act as a opposing force during the power stroke, and the maximum amount of power that we can attain in the power stroke will be reduced because of this. To prevent that, we should be providing a bit of lubrication, and that will be given by the oil, lubricant, different kind of lubricant oils. And what they do is that they need to have two property. They need to have adhesion towards cylinder wall, but at the same time, the other side should be moving freely. So if you consider a plan view of the cylinder piston arrangement, if you consider this to be cylinder and this to be piston, uh, this is not to this is not to scale, but this is only for representative purpose. And this is piston, this is cylinder. So the outer surface will be having some kind of protrusions, and this gap is magnified for showing purpose. So suppose if this outer surface is having this much thickness as of some protrusions, then it can interfere with the piston movement. So piston moves into plane and out of plane, and to prevent this friction from interfering with the power stroke, we will be providing some kind of lubricant, and that lubricant should be having strong adhesion towards the outer surface, that is the cylinder surface, and at the same time it should be moving freely uh, with the moving piston. So if you consider a normal fluid without any viscosity, you can't expect the outer surface to have an adhesion you cannot have the lubricant oil to have an adhesion towards the outer surface. So what we need to have, it should be having strong attaching force to the outer surface, and a strong motion, uh, which it should move along with the piston. There should be no slip along with piston. So a normal fluid with high viscosity will be providing that. So viscosity is one of the important properties of the lubricant. Density, thermal conductivity, and melting point can be compromised. The melting point is not an issue for a lubricant if you are using a liquid lubricant, normal oil lubricants. Because we are operating anyway at a higher temperature, temperatures of order of thousands. 1000 kelvins. So the melting point can be ruled out. Thermal conductivity is a factor. If it is having a good thermal conductivity, it's well and truly good. It's an added benefit. Density doesn't matter. So the most important property is viscosity to prevent smooth contact between the piston and the cylinder arrangement. The viscosity of the oil smooth. It should be having no slip at the piston interface, and adduction towards the cylinder interface. So after lubrication, we will move to fuel injection and fuel supply systems. So which this question, it's a easy question, anyone can answer this. Which of the following is the most widely used fuel system? It's a gravity system, pressure system, pump system, vacuum system. So can anyone answer what is the answer for this type of, which is the type of fuel supply system used in the automobiles? Is it pump-based system or a pressure-based system or a gravity system or a vacuum system?
Research system is used in automobile, sir.
Sir, what was the
Uh,
last question?
Yeah, this one?
Yes, sir.
Yeah. Is it, have you noted it down?
Yes, sir.
Okay, right. Can I move to the next problem?
Yes, sir.
Okay, right. So it's the answer to this problem is not pressure system, it's pump system. So here a steel pipe carries gasoline to the fuel pump, which pumps the fuel to the float chamber through a flexible pipe. So it's actually a pump system that is being used in the SA engines to pump-based system. So if it is for carburetors, the fuel, the petrol will be pumped from the tank to the float chamber, or if it is a MPFI or a gas or a GDI based system, there will be a pressurized line. But normally, if you want to say, you can say it's a pump based system which dominates compared to the other systems. The This is a question regarding the injection of fuel into an SA engine. Which all will be the methods by which a fuel petrol can be injected into an SA engine? The options are direct injection of fuel into the cylinder, injection of a fuel close to the inlet valve, injection of the fuel to the inlet manifold, and all of the mentioned. So which all will be the methods by which fuel can be injected to the SA engine? Yeah,
All of you.
yeah, right.
All of the
Yes, right. So can you please tell me what is the reason for it? Or what are the common synonym of these options? What is injection of fuel close to the inlet valve? What is that?
C number, sir.
Huh?
C number, I guess.
I didn't get you. Can you please come again?
The answer of this question is C. C. Option
No, all of the above, right? It can be done using all the methods, right? So
in spark ignition engine.
yeah.
Option A is not possible, no, sir.
It's possible. So several of the recent methods, GDI, GDI method uses direct injection of a fuel into the cylinder in the SA engine. And similarly, injection of fuel into the fuel very close to the inlet manifold in the MPFI engines, right? So the fuel will be injected extremely close to the inlet valve. So it's also called a port fuel injection method. So that is also one. These are all SA engines. That is also one method, and also injection of fuel into the inlet manifold. So that is a traditional method of injection. So that is the single point or throttle valve injection system is an example of the injection of fuel into the inlet manifold. So all these three methods are possible in the case of SA engine. Also, the traditional method of carburetor, it's an obsolete method right now. We do not consider right now. All the engines will be having either GDI or MPFI or throttle valve injection system. So answer to this question is all of them. So the direct injection of fuel into system, GDI method is there. Injection of fuel close to the inlet valve, that is nearby the inlet valve. It's called port fuel injection system. Or normal terms, it's called MPFI, multi-point fuel injection system. And injection of fuel into the inlet manifold, it's called, in simple terms, it's called single point fuel injection system, or it's also called a throttle valve injection system. So have you understood? Does anyone have got any doubts? Shubham, did you understand? All the methods can be used, right?
Yes, yes, sir. Yes, sir. Got it.
Okay, right. Next is a question. It's a theoretical question. Fuel injection in an SA engine dash volumetric efficiency. Volumetric efficiency should be expressed in terms of air only. So how will the volumetric efficiency be affected by injection of fuel into an SA engine, replacing the old carburetor models? So what will be the answer for this question? Fuel injection in an SA engine increases, decreases, maintains constant, none of the above. Volumetric efficiency, what is the answer? Volumetric efficiency, you should understand it's only for air. There will not be consideration of fuel. So the volumetric efficiency formula is the actual flow rate of air entering the manifold towards the stroke volume multiplied by the number of cycles per second. So for a four-stroke engine, it will be number of revolutions by 2, and for a two-stroke engines, the number of cycles will be in its number of revolutions per second itself. Cycles per second. And we should consider the number of cylinders also in this problem. If you consider a single cylinder, you can use this equation. So how will the volumetric efficiency change if the if you use a fuel injection method instead of traditional methods of air fuel homogeneous mixture formation. Can anyone say? So the answer is it increases since compared to the carburetor models where we mix fuel with air, the amount of air which is incoming reduces. So the actual mass flow rate of air which is incoming reduces. But in the case of injecting methods, fuel will not be mixed with air before the inlet manifold. So the whole volume will be occupied by only air. So because of that, there will be a markable increase in volumetric efficiency. So the answer to this problem is it increases. Yeah. So this question is a qualitative question, which is the most accurate gasoline injection system. Direct injection, port injection, throttle body injection, manifold injection. So direct injection is a normal GDI method. Port injection can be MPFI method. Throttle body injection can be throttle body and manifold injection can be for combinations of single point fuel injection, throttle valve injection systems. So can you please say what will be the most accurate gasoline injection system? Which of the four will be having a comparatively better performance? Which of the following gives comparatively better performance?
Sir, B, I guess.
Yeah, right. Can you
But I don't have any clarification, sir.
okay, right. So the most accurate.
Sir, what was the eighth question?
Yep. So fuel injection in an SA engine increases, decreases, or maintains constant the volumetric
Yes, sir.
efficiency. Got it? It increases the volumetric efficiency. Can I move to the next question? Are you there? Yeah. So the reason is that in the port injection method, the fuel will be injected uh, just besides the inlet valve. So the inlet valve itself will be at a higher temperature, and that will be helping in vaporizing the fuel much before reaching the cylinders. So that vaporizing will be helping in better mixing with the incoming air. So that is the reason why port injection is a favored method. It's a multi-point fuel injection method. So it will be helping, basically it will be helping to evaporate the fuel better. Next is similar question. What is the advantage of fuel injection in an SA engine? So will it be having low initial cost, low maintenance requirement, increased volumetric efficiency, or none of the above? Can you please find out what will be the answer?
increased volumetric efficiency, sir.
Right. So the cost and maintenance is comparatively higher compared to the old systems, but the increased volumetric efficiency is a significant advantage. And also a better mixing mixing of air and fuel. That's also an added advantage. Okay, this is regarding atomizing the fuel. This is a general question. By atomizing so in the normal injection methods, there are two processes. One is atomizing of the fuel, and the second, yeah.
Okay, sir.
Yeah, right. So by atomizing there are two methods in which, so this question is regarding atomizing the fuel into very fine drops. It will increase, decrease, don't know. And what it does is that the whole area for heat transfer increases because we are reducing the volume even further. So more area for heat transfer, better vaporizing, and better mixing. Have you understood?
Yes, sir.
This is a general question. The injector assembly consists of which all parts? A needle valve, a compression spring, a nozzle, and an injector body. All of them mentioned.
All of them.
Right. So can anyone say why a needle valve is used?
Needle valve is used because a very fine droplets are getting into the cylinder, sir.
No, can you please repeat again? I couldn't hear you. There was some issue with the mic. Can you please repeat again?
Needle valve is used because of very fine droplets of fluid are getting into the cylinder, sir.
Right. Okay. So the answer is all of them mentioned. So it's used. It can be used.
Yes.
Can be used for finely atomizing the fuel. A compression spring will be doing the up and down of the spindle. Nozzle, which will be directing the fuel into the air, and then there will be an injector body, which will be having the high pressure fuel in it. So all these will be combining together to form an assembly of injector. All of them will be performing particular duties. And this is a similar question to the previous one. higher, lower, equal the injection pressure, better the dispersion and penetration of the fuel into all desired location into combustion chamber. So what will be the answer for it? How can the injected fuel reach each and every nook and corner of the cylinder? Higher pressure, lower pressure, equal. Yeah,
Here.
higher pressure, right? So the explanation is similar to the previous question. No, the two questions before, right? So higher pressure, the more atomization of the fuel, more surface area for heat transfer, better mixing, and it will reach each and every section of the combustion chamber cylinder, we can say. This is a question which is based on the lecture I guess lecture 9, I guess. Sorry, lecture 13, I guess. If the density of compressed air in the combustion chamber is dash, the resistance to the movement of the droplets is higher. And you would have seen the lectures, and it's mentioned that higher pressure and a higher density is a suitable entity for better dispersion of fuel. So in this particular problem, what will be the density value if you want to have higher resistance to the droplet movement? So droplet and atoms are different. The droplets will be in liquid form. Atom, once it reduces its volume, it will be becoming atoms. And these atoms, once it exchanges heat with the in air at high temperature and pressure, vaporizes. And then because of some swirling in the chamber or the motions in the chamber, it mixes with the air, producing a comparatively better homogeneous mixture of air and fuel nearby the injection area. So in this particular problem, what will be the answer? What should be the density of the compressed air in the combustion chamber if you want to resist the movement of droplets? Can anyone say? So the answer to this problem is density
Yes,
of the huh?
higher density, sir.
Right. The density of a compressed air should be high, such that the incoming fuel droplet will be feeling resistance to its motion, and that resistance will be introducing comparatively higher mixing of the fuel with the surrounding air. It shouldn't be the droplet shouldn't be moving smoothly along with the outside air. We want what we want in this air fuel mixture in the combustion chamber is to have better mixing. Okay, this is also from the lecture 14, I guess. Fuel striking the walls of combustion chamber decomposes and produces dash deposits. One of the design parameters of nozzle is to ensure that the fuel doesn't strike the combustion chamber walls. So, what is the reason for it? Can anyone say what kind of deposits will be formed once fuel strike the walls of combustion chamber?
Carbon, sir.
Yes, right. So when the fuel strike the walls of combustion chamber, the fuel decomposes and produces carbon deposits. So the answer to this problem is carbon deposits. So the fuel will be having, it's a mixture of carbon and hydrogen, right? So only way it can form, only thing which it can form is carbon deposit, not iron or ash or something. Dash losses are caused due to the leakage of combustion products past the piston from the cylinder to the crankcase. So I had briefly touched this in an initial question. So what is the name of these losses which is caused by the leakage of the combustion products from the piston past the piston rings from the cylinder to the crankcase?
Blow by.
Yeah, right, blow by. So
It was
to
discussed before, sir.
yeah, huh?
It was already discussed before, sir.
Yes,
I guess.
right. It's blow by losses, and
Yes, sir.
we use crankcase ventilation to just remove the blow by gases which gets filled in the crankcase. We provide some ventilation. So that was the context of the previous question. The question is repeated. Okay. Dash is the property of lubricating oil due to which the oil particles stick with the metal surfaces.
Adhesiveness.
Yes, right. So one of the earliest questions where we had to have lubricating, where we had to use lubricating oil. I mentioned that the adhesiveness of the oil to the metal surface is one of the important properties of lubricating oil, and also along with that viscosity. And this is regarding frictions. So how will the mechanical friction change vary with increase in speed? You need to be careful in the question. It's speed, not load. The mechanical friction actually it's directly proportional to speed. So it increases with friction increases with the speed. Here one should be careful that I didn't use load in this case, only mentioned about the speed.
Sir, excuse me,
Yeah.
sir.
Huh? Yeah.
It, mean effective uh, uh, is that frictional power, sir? Which we
No. Yeah. That is also there. That will also take into account the friction of the cylinder. But in that case, what we mentioned was that we compared between different loads, right? Full loads and half loads. Here it
yes,
is
sir.
with respect to the speed. So what we considered there was that with respect to the load, the frictional power remains the same. So the brake power vary and correspondingly the uh, brake power vary and correspondingly the Indicated power will also vary. Frictional power remains a constant with respect to load. In one of the previous classes we have studied that, right? Here, but with respect to speed of the engine, friction will be increasing. So the more the more the RPM at which the crankcase rotates, the piston correspondingly will be moving that much faster. Correspondingly, the friction associated with also increase. Understood?
Yes, sir.
This is regarding ignition. Yeah.
All of nature, sir.
Yeah. What are the essential components of a battery ignition system? So battery, ignition, ballast resistor, all of them mentioned. So can anyone of you say which all are the components in an ignition system? No, not just the answer is right. All of them are part of battery ignition system. So have you looked into the lectures of ignition system?
Yes, sir.
So can you please say how many, which all are the main equipments of a ignition system?
Distributor, breaker points,
Yeah.
balance system,
Spark plug, sir.
Yeah, spark plug will be there. Yes, obviously will be there, but uh, behind the background of all these things, we need not look into the spark plug area, but what happens behind, which all things will be there in the circuit uh, behind the spark plug. There will be obviously a battery, an ignition switch will be there, and a ballast resistor will be there.
Yes, sir.
So can anyone say why what is the use of a ballast resistor?
Sir,
Why a ballast resistor is used? Why a resistor is used in a yeah.
To regulate the primary current in order to increase the life of breaker contact points.
Right. So ballast resistor is used to regulate primary current, right? Primary current means current in the primary circuit.
Yes, sir.
Yes. To increase the life of
Breaker contact points.
yeah, breaker contact points. Right. Why is an ignition switch used? Can anyone say? Why an ignition switch is used?
Sir, it's simply the job of switch. Connect or disconnect the ignition system, sir.
Right.
Right.
It's used just for connecting or disconnecting the
Yes, sir.
yeah.
It's simple.
Yeah, connect. And some other features are that there will be some capacitors and there will be some breaker points and there will be a primary coil and a secondary coil. The EMF produced in the primary coil, the variation of the current will be generating a corresponding EMF in the secondary coil. When the primary circuit breaks, the battery voltage will be somewhere around 6 to 12 volt, but the output voltage what we'll be getting is close to 10 kilowatt to 20 kilowatt. So this is done by using the breaking of current using the breaker cam, and uh, correspondingly condenser will be used simultaneously to pass the current in the primary circuit, and the once we break the circuit, the primary current flows to the condenser, and the condenser, once it get fully charged, it will be discharging back the primary current, but the flow will be in different direction. It will be going to the positive charge of the battery, and correspondingly the drop in EMF, sudden drop in EMF, and the reversal of the current will be producing an EMF in the secondary coil, and that EMF will be sufficient to create spark across the spark plug. So the EMF produced in the secondary coil will be in the range of 10 kilowatt to 20 kilowatt, and the triggering point or the driving force for it is the sudden drop in voltage. Sorry, sudden drop in current, as well as the reversal of current once the circuit breaks in the primary circuit. And this 10 kilowatt to 20 kilowatt range EMF, when allowed to pass through a 1.5 to 1 to 1.5 mm of spark plug, produces spark, and that spark will be used for combustion of air fuel mixture in an SA engine. This is a diesel fuel injection system, CI injection case. So what will be the inputs used in electronically controlled diesel fuel injection system? So the options are engine speed, crankshaft position, accelerating pedal position. So how many of you know what will be the process of diesel fuel injection, modern diesel fuel injection systems? What will be the components of a fuel injection system? Take the case of electronic fuel injection. So what will be the components? So there will be an ECU, electronic control unit, and that will be taking input from a lot of things. One is engine speed, and other is crankshaft position. Other is accelerating pedal position of the throttle. And also it will be taking the inlet air temperature, cooling water temperature, cooling jacket temperature, or if you are using a lubricant oil temperature. And also the incoming air temperature, ambient air temperature. And using these inputs, these inputs will be taken to ECU, and the electronic control unit will be checking what will be the appropriate condition right now, and based on that they will be taking a decision, and that feedback will be given to a filter pump system, and that pump system will be regulating the flow of the fuel that will be injected to the incoming air, maybe in an inlet manifold or nearby the port. So based on these inputs, the fuel volume flow rate will be controlled depending upon which case we operate the engine. If it is idling, we need a rich mixture. If it is cruising, we need a lean mixture. If it is accelerating, when we need more power, we need again rich mixture. So based on this, we will be controlling the volume flow rate. So the inputs will be can be engine speed, crankshaft position, uh, accelerating pedal position, that is throttle position, and intake air temperature, lubricant oil temperature, water jacket temperature, ambient air temperature. Okay. By means of EFI, means electronic fuel injection systems, one can achieve the precise control of which all things we can control by using EFI. Can we control fuel injection quantity? Can we control the duration for which the injection happens? Can we control the pressure? So we need to look, right? Which all cases where which all things can be controlled by using an electronic fuel injection? Can anyone please tell? Can anyone say what is the answer for this problem? So the electronic fuel injection systems can control all of them. So in the previous problem, we have seen that fuel injection quantity can be regulated, right? So similar to that, the injection duration as well as the pressure during the injection can also be varied based on the inputs the electronic control unit gets and the feedback it gives to the its electronic fuel injection. EFI means electronic fuel injection. So along with the injection fuel injection quantity, it can also it can also vary the duration of the injection time, injection, as well as the pressure during the injection. So all the three can be varied by using an electronic fuel injection CC. So this is a common question. This is a continuation of what we have seen in the previous week. We have discussed about carburetor, right? So this is a question which we have discussed in the previous lecture also. When a cold engine is started, it requires a dash mixture, linear, richer, chemically equal, none of them mentioned. So what will be the
Richer.
Yeah, it's richer. So we require a richer mixture at the when the engine is cold, because initially only air will be coming in, that is not sufficient to start combustion. So we need to provide more richer mixture. So usually we'll be having choke valve provided in the engines that will be sending in highly rich air fuel mixture. When so it will be in the range of very much less than 15. If it is a case of petrol engine, the stoichiometric ratio is in the is 15.2:1. So for a richer mixture, it will be very much lower than that. In the case of cold engine, cold start. What are the types of multi-point fuel injection system? So multi-point fuel injection systems. Can anyone say what is the answer for this particular problem? Is port injection a MPFA or a throttle valve injection an MPFA process?
The port and throttle body injection.
Right. Both of them can qualify as MPFI. In port injection, we will be injecting the fuel nearby the inlet valve. In throttle body, we will be injecting it just in the inlet manifold just after the throttle valve. Multi-point fuel injection. Yep.
fuel रेल होता है तो fuel रेल के अंदर मल्टी पॉइंट इंजेक्टर तो होता है पोर्ट बा टोटल बॉडी इंजेक्टर तो नहीं समझा सी का
Okay, throttle body injection actually. Port injection is nearby the inlet valve. Throttle body injection is nearby the throttle valve in the inlet manifold. It will not be in the cylinder. It will not be nearby the valve. It will be just like the previous case of carburetor. This injection happens in the inlet manifold.
Okay, समझ गया
But the pressure compared to the carburetor case, the pressure is high since we are injecting the fuel at a high pressure. That's the only difference. Better mixing of air fuel mixture.
Okay, sir. समझ गया
Better atomization and dash will make the engine less knock prone. So this is regarding SA engines. What will ensure knocking is less? Knocking in the case of SA engines happens when the farthest corners air fuel mixture will be detonating quicker than very quickly than the air fuel mixture nearby the spark plug. So they will start to auto detonate. That is knocking in SA engine. So how can we prevent knocking in SA engine? Better atomization and dash can make the engine less knock prone. Right. So better atomization and vaporization ensures better mixing of air fuel mixture, and we can ensure a homogeneous air fuel mixture throughout the cylinder, and so that the spark will be reaching the farthest corners of the cylinder. And thereby we can prevent auto ignition of air fuel mixture nearby the cylinder walls. Right. What is a requirement met by the injection systems? Proper atomization of fuel into very fine droplets, proper spray pattern to ensure rapid mixing of fuel and air, uniform distribution of fuel droplets throughout the combustion chamber. All of the above mentioned.
All of
Right.
D, then D.
Right. So a proper injection system, this is summarizing all the things which we have discussed right now. it should be having proper atomization of the fuel to reduce them to fine droplets so that the surface area increases. And we have to ensure that the spray pattern, so we'll be using different nozzles to ensure that the fuel goes to each and every nook and corner of the cylinder. Proper spray pattern to ensure rapid mixing of fuel and air, and uniform distribution of the fuel droplets throughout the combustion chamber. And better vaporization ensures better mixing, and that will be resulting in better combustion, better uniform combustion. Uh, this is a question regarding quantity of the fuel to be injected per cylinder per cycle. Can anyone please solve it and find out what is the answer for it? It's a case of a 6-cylinder 4-stroke diesel engine. It is developing 125 kilowatt at 3000 RPM. Its brake specific fuel consumption is 200 gram per kilowatt. Specific fuel consumption is in terms of mass divided by the power produced in the cycle. Calculate the quantity of the fuel to be injected per cycle per cylinder. Specific gravity of the fuel is taken as 0.25. So the relative density is 0.85. So can you please figure out what will be the quantity of the fuel to be injected per cycle per cylinder? So in this particular problem, brake specific fuel consumption value is given as 200 gram per kilowatt. And also we know the power developed, the brake power developed by the 6 cylinders together, and the RPM is also given. So we can calculate the fuel consumed by the 6 cylinders together. Then we can calculate the quantity of a fuel taken by a single cylinder, because the whole quantity divided by 6 will be giving the quantity of fuel consumed by a single cylinder. But at the same time, we need to ensure that this is a four-stroke diesel engine. So the number of cycles per second will be equal to number of revolutions by 2. That also we need to take into account. So can anyone try to solve this problem and tell what is the answer for this problem? Has anyone solved this? Yeah. So if none of you have tried it, I'll try solving this problem. So in this particular problem, break specific fuel consumption is 200 grams per kilowatt hour. We know the power developed equal to 125 kilowatt. From this, we can calculate what will be the mass flow rate of mass of fuel consumed. That is equal to 125 kilowatt mass flow rate. Mass flow rate of fuel consumed 125 kilowatt. So the value will be coming around 25 kg 25 kg per hour. And since we have calculated the mass flow rate of fuel, we need to calculate the fuel consumption per cylinder. So this is for the 6 cylinders together. The fuel mass flow rate per cylinder. This is a total value is equal to 25 divided by 6. That will be coming around 4.17 kilogram per hour. And this is the fuel mass flow rate per we need to calculate actually the fuel mass flow rate per cycle. But what we know the number of what will be the RPM, 3000 RPM. So the number of cycles per second will be for a 4-stroke engine will be equal to 1500. So we know that for a 4-stroke engine for a 4-stroke engine number of cycles is equal to RPM divided by 2. So in this case, it will be 3000 divided by 2, 1000 RPM cycles per minute. That will be the number of cycles. What we have to do, we have to find the volume of fuel injected per cycle. In this particular problem, the question shows per cycle per cylinder. So per cycle we have per cylinder we have calculated. Now we have to calculate per cycle. So what we do is that we convert everything to SI units. So mass flow, the quantity of fuel, it's not flow rate, it's fuel in terms of pure quantity. Mass of fuel injected equal to 4.17 divided by, so you convert hour into minutes, it will be 60. 4.17 divided by 60, the whole thing divided by 1500 cycles per minute, we get 4. So 4.17 divided by 60 into 1500, we'll be getting around 0.0463 grams. So this is in terms of gram. We need to calculate in terms of volume. So we divide it by the density. So volume of fuel in terms of cc per cycle, we in terms of cubic centimeter per cycle, we take the mass flow rate 0.0463 divided by the density in terms of relative terms 0.85. We'll be getting the value let me write this in the next page, otherwise it can be confusing. So the volume of fuel in terms of cc per cycle equal to mass of fuel per cycle divided by density of the fuel. So mass flow rate, mass of fuel is 0.0463 grams divided by density in terms of relative terms 0.85. We'll get somewhere around 0.05. 0.0545 gram per cycle. So the answer is the first option. So in that particular problem, we had the brake specific fuel consumption given. We have to calculate the mass flow rate of a fuel based on the power developed, and that value will be for all the 6 cylinders combined together. We find the mass flow rate per cylinder, and then we calculate the mass of fuel injected, from the mass flow rate of fuel by taking into consideration number of cycles per second of the four-stroke engine, and after calculating the mass flow rate of a fuel per cycle and per cylinder, we calculate the volume flow rate using the density, which is given as 0.85. So since the question is given in terms of the value is given, the unit is given in terms of cubic centimeter, we have used the relative density rather than the pure density. This is a question regarding adjusting ignition timing. So this, which instrument is used for adjusting the ignition timing? Stroboscope light, stopwatch, tachometer, accurate clock. So can anyone guess what will be the answer for this question? So ignition timing, the most important reason why ignition timing be adjusted is to prevent knocking. So, if you delay the ignition, there is a very chance that the air fuel mixture nearby the valve might auto ignite. So in certain cases we advance the spark. In certain cases we delay the injection depending upon the conditions. So how does the IC engine control the ignition timing? So it is being done by using an instrument called stroboscopic light. So it's a light emitting device which is connected to the spark plug of the cylinder, and what it does is that it will be setting the ignition timing, and this the other kind of devices like tachometer, stopwatch, accurate clock can't be used for an IC engine. It has to operate at high temperatures and also at high RPMs. So physically a person can't go there and calculate all the three. So that's why the answer for this problem is stroboscopic light. It's a light emitting device. This is the final problem for today's session. Yes. Yep.
And the answer, sir?
Yeah, answer to this problem is stroboscopic light.
Okay, sir.
So yeah, this is the last problem for today's session. We have to calculate air fuel ratio of methane by weight if it burns without if it burns with stoichiometric quantity of air. The chemical formula of methane is CH4. Can anyone calculate this and tell me how much will be the stoichiometric quantity of air? Not oxygen, air. This is the last portion which was discussed. regarding thermochemistry. So in this problem, what we can
Zero
do is
point
that
zero five eight three four.
stoichiometric ratio of air to fuel, mass of air to mass of fuel.
Yes, sir. The answer is 0.0583.
Are you sure? Air to fuel. Try it once. Meanwhile, I'll also try. So CH4 plus, how will you represent air? Air will be represented by oxygen O2 plus 3.6 N2. So in terms of mole fraction, air will be
17.13,
yeah.
sir.
Huh?
17.13.
Okay, right.
Yes,
Answer
sir.
is right.
I was
Right.
calculating fuel to air ratio, sir.
Yeah, that's what I was trying to tell. You were calculating
Yes,
the
sir.
1 by ratio of, right?
Yes, sir.
So yes.
That's why I got
So
right on.
yes. So this is air. Air will be having 3.76 for 1 molecule of oxygen. There will be corresponding 3.76 times nitrogen, and that will be the combustion products will be normal combustion. In a complete combustion, it will be having carbon dioxide, water, and this nitrogen doesn't take part in combustion. It's kind of inert. So only oxygen takes part in combustion with methane. So we should be calculating the number of moles. We should be trying to balance this equation out. So methane O2 plus 3.676 nitrogen will be giving carbon dioxide, water, and nitrogen will be inert in this particular case. We assume that there is no production of oxides of nitrogen, and we are not using any catalytic converters also. So in this particular problem, we will balance out the value of oxygen on both the sides, but for a hydrocarbon mixture of carbon and hydrogen, we can easily calculate the coefficient of the number of molecules, the number of mole requires of oxygen by using the empirical formula. If Cm Hn corresponds to a general hydrocarbon, the number of molecules of oxygen required will be given by the formula m plus n divided by 4. So in this case, m is equal to 1 and n is equal to 4. So the number of molecules is equal to 2. And correspondingly, we balance out on the right hand side. So oxygen 2 terms are taken here, and correspondingly there should be 2 hydrogen molecules, and it's balanced out. And nitrogen, in order to balance out nitrogen, it should be balanced by 2. So this will be the balancing of stoichiometric composition. It's a stoichiometric balancing of air and the fuel. In this particular ratio, we assume there is complete combustion of a mixture of fuel with air, and we are not assuming lean or rich mixture in this particular case. In the case of lean mixture, air will be more. Instead of 2, we will be having more than 2 for air. In the case of rich mixture, air will be lesser than that of the stoichiometric ratio. It will be less than 2 if it is a rich mixture. So in order to calculate the air fuel ratio, and since this is in order to calculate air fuel ratio, and the current condition in this particular problem is stoichiometric, it's equal to mass of air to mass of fuel. So mass of air will be given by 2 into O2 molecules weight will be 32 plus N2 molecules weight will be 28. So 2 into 3.6 into 28, 3.76 into 28 divided by mass flow rate of methane will be 1 molecule of methane multiplied by not mass flow rate, atomic mass of the molecular weight of methane, CH4, C atomic weight of carbon is 12, atomic weight of hydrogen is 1, hydrogen atom is 1. So the total molecular weight of methane is 16. Pardon me if I have used molecular flow rate, sorry, mass flow rate, it's molecular weight. So we calculate the value of the ratio and it will be coming around 64 plus 600. So how much is the value coming? This is coming around 15 point, this is coming around 17.6 or something. So can anyone tell what is the value?
$17.16, sir.
17.16. Let me check once whether my view is right or wrong. Yes, the value is 17.16, right? Right. So that will be the solution. That will be the stoichiometric air fuel ratio of methane. The value is 17.6, 17.16. So this value keep on varying for the kind of hydrocarbon we use. Depending upon the value of the number of molecules of carbon and hydrogen, the balancing terms of air will vary, and based on that, we'll be able to get the air fuel ratio stoichiometric value. So that finishes the session for this week. So in this session, we have discussed briefly about the lubricating theory and lubricants used for IC engines, a few questions regarding them, and few injection based questions we have discussed. Also a few questions on ignition systems, where we have discussed about their the type of the components of the ignition systems, and then the thermochemistry of the fuels. One question towards the end for balancing the quantity of air required for stoichiometric combustion of methane. And yeah, that's a session. And in the next week we will be discussing about the knocking terms, more into SA and CA knocking. And a few questions about that we'll be discussing next Monday. And for Shubham, I have looked into the question which you asked last day regarding a diesel auto ignition case, right? So in the case of petrol,
Yes, sir.
yeah. So for long, it all depends upon the bond energy. For diesel has got close to 10 carbon atoms. Petrol has got 8 carbon atoms. So as the number of carbon atom increases in a long chain, or if it is a straight long chain, or the number of carbon atom increases, the amount of bond energy required to break them is less. So if it is more branched out, or the number of carbon atoms are less, as in the case of petrol, the bond energy required to break them is more. So because of that, the diesel can be auto ignited at a lower temperature. So their auto ignition temperature is close to 2 turn. But petrol is more. Petrol's auto ignition temperature is more because they are much more shorter, straight chain, and bond energy required to break them is more. So they can't be auto ignited just like by increasing the pressure at high pressures in the CA engines. So an extra energy needs to be provided, an extra trigger need to be provided in the form of spark plug. So that is the answer for the question which you asked last week. Yes. You can get the you'll be getting the slides as well as the video of today's lecture. I'll be posting it in YouTube. And simultaneously, the NPTEL authorities will be sharing you with the link once the week is over. All the 3 lectures are over, so you can look into that. Shubham, have I answered your question?
Yes, sir.
Yeah. Okay.
Sir,
Yeah.
one more question, sir.
Yes.
Sir, in the very last question, we discussed, you discussed the reaction, right?
Yes.
Methane, oxygen, and nitrogen.
Right.
But and the hydrocarbon bonds with oxygen, releasing water and carbon dioxide gas, right, sir?
Right. Stoichiometric combustion.
Yes, sir. But you just left nitrogen as it is, sir.
It doesn't take part in the combustion, right? Combustion takes place between oxygen. Combustion means burning in oxygen, right? So
Yeah,
the
yes, sir.
formation of the nitrous oxides, the various oxides of nitrogen are ignored for the current analysis. We take into consideration only the combustion. This is the basic analysis.
Okay, but sir, in practical life, these machines releases NOx particles also.
Right. It releases, the automobiles releases NOx particles. We need to take into account that also in the real equations. For the basic analysis, to calculate the air fuel ratio, we can use this combustion, these stoichiometric equations.
Okay.
Right.
Yes, sir.
So yes. So if that finishes the question, we can meet the next weekend.